So now that I reviewed SVM and how we could use this as a classifier, we'll go back to the ranking example and see how this applies. So I simulated some data. So we have these rankings, Y1 through Y5, and I just keep it simple. I just made them 1 through 5. And then for each of these, there are some features, so these X's. And this is going to be in 2 dimensions so that we could visualize this data. So all right, I don't have a picture of what it looks like. It's not working. But it looks similar to this. So you'd have these 5 different observations plotted in dimensions of 1 and 2. And what you want to do is, this one in the top left would be your first ranking. This would be the second, third, and fourth, and fifth, if I was able to show that picture. But the basic idea is to look at all these pairwise differences. So I would subtract the features of each of these, and then just look at the differences, and it looks like this. So you see all these blue ones are the positive classification. So this is where the first one was ranked higher than the second one. So you see Y1 minus Y5. So these are just subtracting the features and plotting them. And then all these red ones are if you took the other side, the opposite direction, and did Y2 minus Y1. So these would all be classified as the first one being lower than the second one being lower than the first one. And then you can see how this breaks into a classification problem once you look at the differences. So really, you only need half of these points because this is symmetric, and you could, if you were using the optimization algorithms, you would just use half, but I kept them all in there to make it easy to just plug into R and let R figure it out. And you could also see that some of these observations are really easy to classify. If you're looking at the first and last term of this ranking list, they're all the way up in the upper corner. It's really easy to classify as 1 being ahead of 5. These ones near the margin are 1 and 2, 4 and 5, so these ones are closer together. Those are harder to classify. So what we're going to do is we're going to fit an SVM and get a training rule for new observations, and then apply that to those new observations and see how to classify them. So this is how you would fit it in R. You have this creatively named package E1071, and you just fit it using the SVM function like you would a linear model or GLM, and you specify what kernel you want to use and then the tuning parameter. So this is the cost. An easier way is to figure out what cost to use, there's this tuning function. So you could just specify a whole bunch of parameters. So here I specified 9 parameters for costs. It'll run them all and perform cross-validation on each of those and spit out the best model to use. Here I'm just using a linear kernel, but if you use radial, you could also specify different gammas, and it'll run all of them and tell you the right parameters to use based on cross-validation.
What's the metric for the cross-validation? Is it Kendall cloud we're looking at?
No, here they're just using classification error.
Oh, okay.
So here I'm just doing classification. This data frame I'm using are all the pairwise differences. So I'm just trying to classify the differences. And then I could just pick out the best model, and that's my fit for the SVM. And if you plot it, this is what it looks like. So these are all those pairwise differences I showed. So all the black ones are on the blue side, all the red ones are on the pink side, so they're all correctly classified. And then you could see some of these are X's. That means it's a support vector. So these X's are the only ones influencing this margin right here. So it works really well on the training data. We would be able to look at that and perfectly come up with a ranking, but we want to try it out on some testing data. So I generated another ranking of Y1 through Y5, the same way I generated the first set. And then I'm just going to fit that to the SVM. But the problem here is I'm going to take this decision rule that I used before. So for classification, you would just look at the sign of this decision rule. And if it's positive or negative, classify it one way or the other. Here I'm actually going to take the value that it spits out. So I'm going to call that the decision value. And then I'm going to use those values to rank the items that I'm fitting. So it seems a little weird that I'm doing this because I use the model trained on differences, but then I'm actually going to plug the X's directly in when I'm to the fitted equation and get these values in order based on that. But what it's really doing is you're comparing it to this virtual observation that has 0 for all the x values. And then once you compare everyone to this virtual observation, you know which order they should fall in compared to that one. So that's really what it's doing. So here's the testing data. It looks similar to what the training data would have looked like if you saw it. But what the real ranks here are is you have the first one in the top left, then it's third, second. So you could see a trend of how the rankings are fitted to this feature space. And then this is what it looks like when you plug it into the SVM fit. So the actual rankings are 1 through 5, and then the predicted are mixing up 2 and 3. They seem out of order. So the correlation for this, the Kendall's tau, would be just 0.8. Any questions on that? So all we're doing is looking at pairwise differences of a ranking and training a classification model and using that to predict new values and sorting based on those values.